Bismillahirrahmanirrahim. Hi, this is my video number 20. Okay, my video number 20. So in this talk I will try to talk a couple of theorems, try to prove some of them. Okay. First, we look at the quite important theorem in integral equation, which is riesz-fischer theorem. Yeah. Riesz-fischer theorem. So what is a riesz-fischer theorem? So we let the sequence phi I x be an autonomous system, autonomous system of L2 function define and integrable together, and define and integrable with the square of the moduli with the square of the moduli in the domain AB, and alpha I is a sequence of complex number, is a sequence of complex numbers such that ai squared, alpha I squared, alpha I1 to infinity converge. Then the theorem says that then there exists a unique function, exists a unique function fx for which the number alpha, for which the number alpha I are the Fourier coefficient, with respect to the autonomous system, that phi I x, and to which the Fourier series converge in the mean, and to which the Fourier series converge in the mean. That is what all those things say is that if you take the norm for f minus summation of alpha I phi I from 1 to infinity, right? This goes to 0, Sn goes to infinity. So that's the riesz-fischer theorem. Now we're going to prove this. Yeah. So the thing is that we need to prove that the convergence, all right, the existence of f that make this series converge. We take the norm of that is converge to some to 0. Yeah. Okay, so let's prove this. Okay, let Sn be denote the partial sum of the generalized Fourier series. Yeah. Let Sn x denote the partial sum, denote the, we have partial sum of the generalized Fourier series corresponding to fx, yeah, that is, so when we say partial sums, yeah, partial sum, I hope you understand what partial sum is, which means that Sn can be written as summation of I 1 to n phi I psi I x. That means the partial sum. And of course, if the partial sum converge, then that phi is also, the series also, the sequence is also converge. Okay, then the sum, yeah, Sn, then Sn x converges in the mean to fx, yeah, over interval AB if we take a limit of n goes to infinity from A to B. We have fx minus Snx squared dx that equal to 0. Okay, so what happened now? If you consider, all right, we have n to n plus 1, n plus 2, and so on up to n plus m, and we take the difference from Sn, see what happened. Now, if you integrate the limit, this limit, all right, S n plus m x minus Sn x squared dx. Okay, so what left is the terms an plus 1, an plus 2, and so on. Yeah, because this is our Sn, so Fn, if you want to put Sn plus m, so this is alpha I phi I from 1 to n plus m. All right, then if we subtract that and that, what left is alpha phi with I from n plus 1 to n plus m. So we have this thing, that, so that gives us All right. The alpha I, phi I, we denote as AI. So therefore, for the alpha n plus 1, so we have a n plus 1 squared, yeah, plus a n plus 2 squared, and so on, until you have a n plus m squared. And since alpha I converge, that's given in the theorem, yeah, since that series I 1 to infinity alpha I converge for every epsilon positive, then there exists arbitrary small number, then there exists a small number lambda positive such that Sn plus m x minus Sn x that less than epsilon for all n greater than delta and n greater than m. I think you are familiar with the proof of this. This is a basic calculus, all right, on the convergence and of series. Yeah. Then there exists, does there exist a unit function f? Then there exists a unique function f integrable in the domain, okay, integrable in AB with squared, we have squared here, okay, with squared of its modulus to which the sequence, that sequence converge. Yeah. So we have, with this we have that sequence Sn x converge in the mean, in the mean. Right, and again you need to show the we have the convergence, yeah, of the whole things, because here we need those things here. All right. So again, since the number alpha I are Fourier coefficient, since alpha I are Fourier coefficient, the Fourier coefficient, yeah, of function f with respect to the autonomous system phi I. So therefore we have the norm of f minus sum alpha I phi I for I from 1 to n, norm of this. We have shown this in the previous proof, I think, relating to somewhere Minkowski or Bessel inequality. Yeah. So in that proof, so this equal to we have f squared plus sum of alpha I minus ci. Yeah. This goes to 0 as n goes to infinity. So I from 1 to n. Then from here you can use the Bessel inequality, yeah, using Bessel inequality. We have alpha I minus ci that equal to a to b f x phi I x dx. Okay, thus it follows that the Fourier series, that ci phi I x of function fx with respect to the autonomous system phi I x, yeah, convergent in the mean, yeah, is convergent in the mean. So which means that f minus some alpha I phi I that goes to 0 as n goes to infinity, I from 1 to n. So that's the proof of riesz-fischer theorem. Next, we look at the couple of other theorem. Theorem that related to symmetric kernel. Theorem that related to symmetric kernel. The proof is not difficult. This one. All right. So let the kernel K xt be symmetric. Okay. Then all iterated kernel is also symmetric. Then all is iterated kernel asymmetric. Yeah, so the proof of this is not really difficult. You need to use mathematical induction, right? So I'll show you the proof. So proof. Okay, first we define what is iterated kernel. We know that iterated kernel, that the symmetric, first thing is the symmetric kernel. The symmetric kernel is K symmetric kernel. Symmetric kernel, which means we have K Tx, this is equal to K xt. And then we define the iterated kernel. We have the iterated kernel, K1 xt, this is K xt. And we define the n terms of K n xt as integrate from a to b K xz K n minus 1 zt dz, yeah, for n 2, 3 and so on. So we prove by mathematical induction. So for the n equal to 1, for the case of 1 here, yeah, use mathematical induction. Use mathematical induction. What is mathematical induction? You need to show for n equal to 1. This is true. Then need to show for n equal to n. This is also true. Then we need to show it's also true for n equal to n plus 1. If this is satisfied, for all cases, then we can conclude for all cases also obey the same principle or the same what is it, the theorem is proof. Okay, so let's try this. So for the k1, or for n equal to 1, or k1 here, for n equal to 1, so k1 xt, this is equal to k tx, because the kxt is equal to k1 xt equal to kxt. Alright, and which means if we take the conjugate of those, so we have k1 tx, this is equal to k tx. Okay, this by definition of iterated kernel. Okay, and then we use the symmetric properties. We have k1 tx, this is equal to k xt. Hence we have from there k1 xt, so we have k1 xt tx bar, this is equal to k1 xt. So therefore it's true for k equal to 1, which is we show that k1 is symmetric. So with this shows that k1 is symmetric. And then for k2, n equal to 2, so for k2, so we have for k2 we have k2 xt, this is equal to from here, okay, from this. So k2 xt, we have integrate a to b kxz k1 zt dt, okay, and k1 we use the iterated kernel, k1 is equal to k. Alright, so from there we have integrate a to b kxz kzx zt dt, okay, k1 zt, so kzt, and then this equal to integrate a to b, this is you can write as a k bar zx, okay, and this one you can write k bar tz, okay, dz, okay, and this k bar you can just simply change the position of those. So what we have ab k bar tz k bar zx dz, and this is equal to integrate a to b ktz and this is equal to k1 zx dz. So this is equal to k2 bar tx. So we have shown from here k2 xt, it can be written as a k2 bar xt. Next, we show for n equal to n plus 1. Alright, we have shown it's true for n equal to 1. It's true for n equal to 2. Alright, and then we try to look at n equal to m. So we suppose Kn xt is symmetric for n equal to m. So which means we have a Km Tx bar, this is equal to Km xt. We can do this because we suppose Km is symmetric. Now for n equal to m plus 1, which is we want to show that Km m plus 1 Tx bar, this is equal to Km plus 1 xt, which is symmetric. Okay, so that's what we want to show. So thus we have a K m plus 1 xt, okay, using definition of iterated kernel. We have a to b k xz km zt dt dz. Okay, and this is equal to a to b k bar zx, that one km bar tz dz, and this is equal to integrate a to b. So we have km tz, we just change the position, so we have km tz, then k bar zx dz, and this is equal to k m plus 1 bar tx. So we have shown that km plus 1 xt equal to km plus 1 by tx, which means km plus 1 is symmetric, which means km plus 1 xt is also symmetric. Okay, so hence by mathematical induction we can say that the iterated kernel for all values of n are symmetric. Yeah? So therefore you can come up with the conclusion Kn Tx bar, this is equal to Kn xt. So they are symmetric. Then I just did the theorem that we already proved I think a couple of lectures back. Yeah, the eigenfunction of the symmetric kernel corresponding to different eigenvalues are orthogonal. So we have proved this theorem. Yeah, the eigenfunction of a symmetric kernel of a symmetric kernel corresponding to different eigenvalues are orthogonal. Corresponding to different eigenvalues are orthogonal. Okay, we have proved this theorem. Also, we have another theorem also has been proved, that the eigenvalue of the symmetric kernel are real. Yeah? The eigenvalues of a symmetric kernel are real. This also has been proved. Next, we'll look at that other theorem. I think you can read this the proof of the theorem in my notes, because I've written quite detail all those things. All right. So I just put the note here. So look at this theorem. The multiplicity of any non-zero eigenvalue is finite for every symmetric kernel for which this finite. Yeah, this is finite. So the main point is that here the multiplicity of any non-zero eigenvalue is finite. So the proof is given here. You just need to show that the multiplicity of the non-zero eigenvalue is finite. So we need to show those things. So if we let phi1 lambda, phi2 lambda, and phi n lambda be the linearly independent eigenfunction corresponding to a nonlinear eigenvalue lambda, then using Riesz-Smith procedure, of course, you're given any eigenvalue, you can make it using the Riesz-Smith procedure, Riesz-Smith process, right, to write in the form of autonomous system. You can do that. So its corresponding complex system also form the autonomous system. So now if we let the kernel is of that form, kxt ai ui lambda bar, where ai is given as this, I think you are familiar with that, we're already familiar with that. Then be the series associated with the kernel k for a fixed x. Yeah. Then we apply the Bessel inequality to this series. The Bessel inequality, we have the integration of some k squared less than or greater than the summation of those. Yeah. And then using apply the Bessel inequality to that. Okay, so we have those things. So integrating with respect to x, that what we have, then we integrate again. So this we have integrate double integration here, at dx dt, and on the right side we have that, and then the rest with summation, because this is autonomous, so it give you 1, so we sum up from 1 to m, so that gives you m over lambda squared. Okay, so in this case the m is the multiplicity of lambda. Now the left hand side, which is our k 2 to 1, is finite. I think left side of this is finite, so therefore m is finite. Yeah, this should be, that one is finite, so this is not 1 to 1. Yeah, for that left hand side is finite, so therefore m is finite. So we have proved that the multiplicity is finite. And we have, I think, one or two more theorem. Let me just read those things. Okay, so next theorem is the eigenvalue of the symmetric kernel. The eigenvalue of the symmetric kernel form a finite or infinite sequence with no finite limit points. The proof is given there, is from the previous proof. We have those things, and then I think you can just proceed that. Some typing error there. So n tend to infinity, those things. The next theorem, the sequence of eigenfunction of a symmetric kernel can be made orthonormal. Again, when you see this orthonormal, you can use Riesz-Smith process. Okay, and the set of eigenvalues of second iterated kernel coincide with the set of square of the eigenvalue of the given kernel. So you know the given integral equation, you can always write in term of operator that I've explained in the previous video, I think. Right. So what we want to show here is that the eigenvalue must be of like this, lambda squared, so it's square. So it's proof in this theorem that lambda, we have lambda square here, so you can proceed further. So I think I stop here for this video. You might not comfort with the content of this, because it's just about theorem and proof, and it's not really easy. You cannot see it directly, yeah. But hopefully, I think later on we can use wherever when needed. So all those theorem we can apply when it comes to the place where we want to use. Okay, so I think I stop here. Thank you. See you in the next video.